Hi guys, so today I'm going to be going over hypothesis testing. So I'm going to be doing 3 questions. I'm going to do 2 just normal binomial distribution ones, and then I'll do a critical region one at the end. But all of the questions I'm doing are 2-tailed, but I will also explain 1-tailed as well. So first of all, feel free to pause the video to read this question, but I'm just going to be going over it at a normal pace. So I always start by giving x, like the test statistic, declaring it. So what I'm going to do is let x be the number of eggs out that have a double yolk out of, it's going to be out of 50 because it's a sample of a random sample of 50 eggs. So next I'm going to move on to the actual hypothesis. So I'm going to set up the null hypothesis, which is 1 egg in every 50, so the probability is 1 over 50. The alternate hypothesis is going to be p is not equal to 1 over 50 because it says it's changed. And if it said it was higher, then you'd put a greater than symbol there. If it was lower, then you'd put a lower than symbol there. But because it's changed, I'm just going to do probability is not equal to 1 over 50. Then it's always helpful to write down your level of significance. So alpha is equal to 0.1 here, but because it's 2-tailed, you split it in half, so alpha is equal to 0.05. You can also put it as 5%, but I'm just going to write it as 0.05. Then you always have to assume that the null hypothesis is true. So you can set up your binomial distribution. So then x, we already declared what x is over here. So x is distributed binomially, is n here and then p, so the amount is 50 as I've already circled. And keep in mind that it's the sample here, not due to the probability being 1 over 50. So then the probability is 1 over 50 because you've assumed that is true. So then if we actually look at the question, in the actual sample, 3 of the chickens laid eggs with double yolks. So we can move on to actually finding the probability. So what I'm going to write here is the probability of eggs being greater than or equal to 3. And the reason why I'm writing that is because of the 3 right here. So that's from the actual sample, and the reason why it's a greater than or equal to symbol is because if you look at the actual sample, the random sample, the 3 out of 50 is greater than 1 out of 50, right, which is the assumed probability. So there's no way this could be the lower tail when you're receiving a higher probability than what you're assuming. So once we have this, binomial distribution is going to only be less than or equal to, right? So we're going to have to change this to 1 minus p x is less than or equal to 2. Hopefully you understand how that works. I can explain that in the later video if you want, but if I put this all into my calculator, I'm going to go to the binomial CD function. I'm going to put in x is 2, n is 50. It's helpful because you can just look at the distribution you've set up. So we have n is 50 and p is 1 over 50. So then once you've all put that into your calculator, you should get 1 minus 0.92157. I usually go to 4 or 5 numbers. You can go to more. I wouldn't recommend going to like 3 or 2 because that's too little. But if I actually work out what this is, it's going to be equal to 0.0784. Or at 5, I meant at 4. So as 0.07843 is more than alpha, which is 0.05, there is not enough evidence to reject H0. Now, this is because the way I imagine this is the significance level as like a gate. So if your number is too small and weak to destroy the gate, then it doesn't let you in and it rejects you. But if your number is really cool and big and it destroys the gate, then it accepts that you're really cool and lets you in, so it does not reject the null hypothesis. If your number is too small to destroy the gate, then you get rejected, then you reject the null hypothesis. So in this case, 0.075 absolutely destroys this 0.05 gate, so there's not enough evidence to reject the null hypothesis, so accept h0. And you should always write it in this format, unless you're doing critical regions, which I'll move on to in a bit. Okay, so moving on to the next question. I am going to skip all of the long intro bit, but I will explain it. Okay, so I've just written the first bit here. So X is the number of correctly diagnosed patients out of 75. The significance level is 5% because you cut it in half because it is a two-tailed test. And the reason why it's a two-tailed test, if you look at H1 here, a manufacturer suggests that a cheaper test will have the same probability of success. So this H0 is the probability of the cheaper test having the same probability of success, right? So it doesn't mention increase or decrease. So an alternate to it being exactly equal to 0.96 is going to be P is not equal to 0.96, making this a two-tailed test. I know this wording is quite confusing. It took me quite a while to understand, but if you ever get something like that, it is a two-tailed test. So moving on, we're going to assume H0 to be true. So we can set up our binomial distribution now. So X is distributed binomially. It's going to be 75 because 75 patients in the sample, and the probability of success is 0.96. Right now, to see what tail we're looking at, we're going to look at our values here. We have 63 and 75. So if I do 63 divided by 75 on my calculator, I'm going to get a value of 0.84, I think, which is less than the 0.96, right? So this is going to be in the lower tail because there's no chance this could be a higher probability than this, right? So let's just check the lower tail. So probability of X being less than or equal to 63. So because it's less than or equal to already, we can just straight away put this into our calculator. But say this was a one-tailed test. If this was a less than or equal to symbol here, it would also be the same for here. And if it was a greater than or equal to symbol, then it would be the same here as well. And then if it is the greatest than symbol here, then you have to do the weird thing with the 1 minus and then the minus 1. But if I just go into my calculator and go to binomial CD, I'm going to have X as 63, N as 75, and P as 0.96. And you should get a value of 0.0000041743. And that, using my example before, so as 0.0000041743 is a lot less than 0.05, it cannot break this barrier right here, so it cannot be accepted in. So there is enough evidence to reject the null hypothesis. Therefore, we accept H1. And then you have to put it into context. So the cheaper test does not have the same probability of correctly diagnosing patients. And that is a full question. So I'm going to be moving on to critical regions now. So here is the question. The start of all of these questions are basically all the same, so I'll skip that again. So see you guys in a second. So I've just written everything up. It's out of 50 people. It's a two-tailed test because it says that the probability is different from 0.2, not greater than or equal or less than. So we've assumed that the null hypothesis is true, so then we get this distribution here. So because I'm doing critical regions now, and it wants me to find the probability of each tail as close as 2.5 as possible, I'm going to set up this probability here. That probability that X is less than or equal to C is going to be approximately equal to 0.025. If this was a one-tailed test, then I would do either a greater than or less than symbol here. So make sure you rearrange correctly with those if you do have that. But here is a two-tailed test, so we have to find two critical regions. So now we have to go to our formula book to find the distribution chart. So make sure you keep track of the 50 and 0.2 here, and it has to be as close as possible to 0.025. So if I go to the formula book, let me just find n is equal to 50, should be here, and our probability is 0.2. So if we look down here, we need to find the probability that's closest possible to 0.025. So I'm not too sure which one that is out of these two, so let me just write that down. So I've just written the two differences, like with the values on the table, and this one is definitely a lot closer to 0.025, right? Because the difference between them is a lot smaller. And just a tip, if you get your answer in terms of standard form on your calculator, you can just go to Eng notation, engineer notation, which you can then set to 10 times 10 to the power of 0 to find the exact number, which is what I usually do. So because we know it is this value right here, we know that we know that x is equal to 4, right? So from this, we know c is equal to 4. Then if we look at the upper tail, we have p is greater than or equal to c, right? Which would be approximately equal to 0.025. Then, because we can only do it in terms of less than or equal to, we can switch this to 1 minus p x is less than or equal to c minus 1, right? And that would be, again, equal to this. So, if we rearrange this, we're going to get p x is less than or equal to c minus 1 is approximately equal to, because we move this over here now, so we're going to move this over here, so it would be 1 minus 0.025, which is 0.975. Now this is where doing it in one-tailed tests comes in really important, because if this was a greater than equal to symbol, when you move this over to here, you see how this sign stays the same, but this is now less than this, so always keep that in mind. But anyways, now that we have this distribution here, we can go back to our table and find the closest thing that is equal to 0.975, which should be this here. I can tell just from looking at it that it's this one, so no need to work it out. So then that would mean that the c minus 1 value is equal to 15, because it was 15 on the table, right? So then that must mean that c is equal to 16. So then we can write our critical regions, which would be x is less than or equal to 4, or x is greater than or equal to 16. And that would be because of the 16 here corresponds with this here. You can write it as C1 and C2 if you prefer, but keeping it as just C is fine as long as you can understand it. So moving on to part B, it wants us to find the exact significance level of this test, also known as the P level. So I've just written that C was equal to 4 and 15, or C minus 1, but we use those values. So if we go back to the table, we had 0.9692 and it was 0.0185. So because this was the higher value here, we do 1 minus that to find the actual probability of that. So then if you put this into your calculator, you get 0.493, which is equal to 4.93%. So now moving on to part C, because our regions were these, and it says 15 people by that certain make. So because 15 does not lie in any of these critical regions, because 15 is not less than equal to 4 or greater than equal to 16, it means that it's not in the critical region. So my conclusion would be, as 15 does not lie in any critical regions, the probability of people buying a certain make of computer is 0.2. If it did lie in the critical region, then we would say the probability of people buying a certain make of computer is not equal to 0.2. So that is all of the questions. Let me know if you have any more questions in the comments, but try my best. Sorry if my handwriting is terrible.